So my name is Tariq King. I'm the head of quality at Ultimate Software. And this is my first Codecamp. This is amazing. Again, thank you to the organizers. This is awesome. You know, the most awesome part about Codecamp is the price, right? That's incredible, right? I've never seen this before, free of charge, amazing, right? But it does cost for organizers to put on an event like this. So please, let's just put a round of applause again for our partners. And so today we're going to talk about the rise of the machines and artificial intelligence and testing. And, you know, artificial intelligence is kind of everywhere, and part of this is to just also bring awareness to the fact that we need to be leveraging this technology in whatever we do. As the head of quality, obviously testing is a big part of that, but testing is a lot more, quality is a lot more than just testing. And we're going to jump right into it. You know, originally when I created this talk, it was for an hour. So I've taken an hour's worth and kind of shrunk it into 30 minutes to give you the essence of it. So let's go. All right. So manual testing. And I actually hate this term manual testing because from my standpoint, all testing is manual, and so we'll talk about that. But at the core of testing, it is really about checking specific facts about the software, right? But to be able to check specific facts about the software, we need to be able to learn about the software, run experiments. We have to do all this work that usually involves the human. And the sad part is that when we start talking about automated testing, a lot of this learning, modeling, experimenting, and so on and so forth is usually forgotten. In other words, we talk about automation, but what are we really automating? Well, when we talk about automation, we really have to still sit down and someone has to learn about the software, has to understand the requirements, and then has to sit down and design test cases. All this stuff is happening manually, right? In other words, back in the 1950s, when the manufacturing discipline started thinking about automation, they were thinking about machines that can operate independently without human presence. And they talked about this idea as lights out manufacturing. We can turn the lights of the factory off, and we can still run. But our philosophy when it comes to testing is not a lights out philosophy. It's far from a lights out philosophy. You can't, because the human is needed. Because after you create those test cases, then you have to manually encode them using Selenium, or if you're doing lower level testing, some XUnit style framework. And then the automation comes, right? You automatically click a button and it runs. And maybe it records or logs the results. But as soon as that execution finishes, guess what? The human being comes back into play. And we have to manually try to determine, is this a real error? Is this a real issue? Is this just a flaky test? And so our idea of automation is really, really warped. And this talk is about thinking about, can we get closer to a true view of automated testing? And so I'm going to tell you a story, and I'm going to tell you the story from the end, right? In other words, game over. Manual testing has already been terminated by artificial intelligence. Because you see, for me, if this is our world here, then this is software. Getting some clicking issues. Cool. And software is really just already eating our world. And if software is eating our world, then this is artificial intelligence and machine learning. And AI and machine learning is literally going to eat software. And when it's done eating software, guess what? All eyes are on us. So are you guys scared? Are you guys scared a little bit about AI and the AI takeover? And who's scared? Let me see who's scared. A few people. Who's terrified? Who's really happy? We're really happy. Like, yeah, finally we're doing something. All right. So, when we look at Hollywood, they really try to make us feel this fear, like Terminator, end of the world. Like, this is done. And to some degree, we need to worry about that because we need to make sure that these systems are dependable, that we can trust them. And again, that kind of relates to testing and getting information about the different types of risks. But it's not all the end of the world, right? I mean, actually, there's a lot of fun pieces of artificial intelligence. And actually, where we started was games, right? And particularly, back in 96 and 97, we had IBM's Deep Blue defeat world chess champion Garry Kasparov. And this was a big deal. How did this happen? Like, how did the machine beat the human? Well, back then, it wasn't actually anything very profound. It was really about brute force computing. You see, like, Deep Blue had dedicated hardware, and back then could process what was a lot of moves per second, probably about 200 million with that hardware. And by brute force, it was able to defeat Kasparov. And to understand this, we have to look at the area of artificial intelligence related to game trees, right? And so we could think about a game like tic-tac-toe, which is a very simple game to think about. And you could enumerate all of the states of this game, and starting from the start state, and all of the possibilities from there. And then from each of those possibilities, once you have that tree, you could determine, well, in a given state, what is the best move to make to get to the outcome that I desire? And if you had enough computing power, obviously, with Deep Blue, you could now start to apply that principle to chess. And of course, the game tree for chess is a lot more complex and a lot more complicated. But with the hardware, and in some cases, Deep Blue would analyze and look at the game tree and look anywhere between 6 to 8 to as much as 20 moves ahead. And so that was able to be enough to defeat Kasparov. So brute force. And we continued in 2010. IBM's Watson project was still playing games, right? Watson was designed and initially applied to play Jeopardy. And this was cool. I mean, if you ever watch Jeopardy, I mean, I like Jeopardy, but it reminds me of how limited my knowledge is when I sit down and folks are, answering these questions. I'm like, how do you know all that information, right? And of course, it's just easier sometimes for a machine to store information. It doesn't, have problems recalling things like we do. But there's a big challenge around here. It's just natural language processing. How do you really interpret these things and answer? And Jeopardy was a game that represented a challenge for computing. And Watson was able to defeat two of the best Jeopardy players, one that had the longest winning streak and one that had the highest earnings. And so we keep seeing artificial intelligence defeat humans at things and become better and better. And now Watson is all over, right? Every area that you can think about, whether it be medical, finance, retail, it's all over our lives. And we're seeing these applications of the machines solving problems and helping humans to do things more efficiently. And this is no different. We always have used technology to become more efficient and become better. And more recently, in 2016, we had a very big breakthrough. And this was where the DeepMind project, Google's DeepMind project, AlphaGo, defeated one of the best professional Go players, Lee Sedol. And you might be asking, well, what was so significant? Right? Well, you already beat someone at chess. What's so significant about Go? Go is an old Chinese game, and if we compare Go to chess, we can start to get an idea of some of these differences. And so chess has 16 pieces, and in terms of the different types of pieces, there's 6 piece types, which is about 35 possible moves, 80 possible moves per game, and the goal here is to capture the opponent's king. All right? Now, Go is actually simpler in terms of the start state. There's actually just 0 pieces in the start state, and there's only 1 piece type, and it behaves uniformly. And the difference is that now you have this explosion when it comes to the number of possible moves, the number of possible moves per game. The goal here is to try to capture as much of the opponent's territory. And to give you an idea of the scale of the difference, right, in terms of the number of possible games that can be played, with Deep Blue in terms of chess, that's 10 to the 120, while with Go, you're talking about 10 to the 761. Now that number is more than the number of atoms in the universe. And so if we wanted to apply brute force, we actually couldn't. We couldn't use the same technique to beat Go as we used to beat chess. And so what was the answer? Well, the answer was something that you might be familiar with by now called deep learning, and actually in particular deep reinforcement learning, which is a form of machine learning. And so now we were at a point where the machines were able to learn. Well, what does that really mean? Well, one of the key ways that I like to describe this idea and think about this, and machine learning has been applied to many things, and now we're doing crazy things like driving cars, and kind of makes us pay attention to what is going on, because now we're really trusting it with our lives, right? I get nervous going on a plane, but statistically it's even more risky to get in a car and drive, right? And so the machine doing that is really tricky. And the way that this works is that these things start off not being very good at this given task, and then they get better over time. And that's what we mean by learning. But in case it's still not very clear, let's walk through what I think is the best way to get people to understand machine learning. This is my definition here, right? The science of getting computers to act without being explicitly programmed. And the core of that I like to think about is, my 5-year-old daughter, Soraya. And Soraya, if we start to think about, and as she's growing and I'm watching her learn, if I start to think about like how she learns to act and I compare her to a robot, there's some key differences. The first one is that traditionally robots have been programmed to follow instructions. Soraya does not like to follow instructions. How Soraya learns and learns best is she learns from experience, right? And in this particular photograph and in this particular photo session, and as a side note, if you ever decide that computer science and software engineering is not for you, become a photographer, because you have to pay so much money for a set of photographs that it just becomes a lucrative thing to do. So just note that. That's my mental note for me in case this doesn't work out. But now we're talking about the machines having experiences. And so what does it mean for a machine to have an experience? And well, the answer is really in the data. You see, we can represent the experiences of a machine as data. We can say, hey, these are examples of raindrops. And here's some things that are not raindrops. And the machine, encountering something new, some new experience or a new piece of data, can now just kind of take a guess, right? Like, hey, I don't really know. I got some examples over here, some examples over here. This looks like it's a raindrop. Or I could have gotten it wrong. It doesn't matter at that point in time, because what you're trying to achieve is learning, right? Like this type of classification is what the machine is trying to achieve. And actually, the machine didn't actually need to know the concept of a raindrop. It didn't need to know that domain concept. You could have just told it, like, here are some things, these are what they look like. Here are some features that I'm looking for. Here's some characteristics of some things that I'm looking for. And here's a bunch of data. And now I want you to separate this data, right? And separate it into these different clusters and, tell me, like, what belongs to what. So these blanket categories, and the machine is able to then do clustering. Now, if the machine gets it wrong, and this is what happens with the idea of reinforcement learning, if the machine gets it wrong and it gets that feedback later, like it takes some move and it doesn't know if that move is good or bad, right? And then later on, it wins the game or it loses the game, and then you assign it a reward after the fact. And then it can get better at new examples as it moves along. All right. So if a program can improve how it performs some given task based on past experience or past data, then you can say the program has learned. And so that's machine learning. There's different types. We just mentioned supervised learning, where you have the data that's labeled, so you know what it is up front. You have an understanding of that domain concept. You know the outcome. And so here you're learning based on known patterns. We're teaching the machine to learn based on those known patterns. The other type is unsupervised, where you don't have labeled data, you don't have knowledge of the outcome, and this is really good for discovering unknown patterns, right? You're learning these patterns from the machine. You give it all the logs and say, hey, here's some features that I'm looking for, or maybe it just starts to cluster things saying, these look similar, these have similar features, and you start to learn from the machine based on that. And then there's this idea of reinforcement learning, where we're generating data through actions. We're trying things, and we really don't know, right? This kind of quasi-state of, being unsupervised in that sense. And then later on, you find out, right? You get feedback. You get feedback on the quality of your actions, and then you're really now learning by trial and error. All right. So it's still really awesome that, like, our brain is still one of the most powerful models of computation that there are out there. And this whole idea of neural networks artificial neural networks is loosely based on the human brain. And what are we doing here? Well, we're saying that there's just a set of inputs, right? That somehow we have outputs that they need to map to. And there's this, like, magic box in the middle. And we'll just call it a magic box for now, right? Because even our own brains seem to be some magical box that we haven't really figured out. And so, upon some input, you try to see how well it maps to the output. And it may not map very well. In other words, like, at first it may be horrible, and you might either give it some reward or you punish it, right? And so you're trying to, with the artificial neural network, try to simulate, like, human judgment. You want it to become better and come closer to the right answer. And one of the ways that you kind of do that is that you evaluate how close it has been, and then you try to modify that internal box, right? You use some weights and you adjust some weights, and maybe it gets closer to the box, and that's how it learns, right? But you're training it in this manner. So, what does all of this have to do with software testing, right? And that brings us to Act 2. You see, in Act 2, we're looking at testing as the main thing that we're concerned about. And right now, the current techniques that we have when it comes to software testing don't give us much benefit when it comes to the testing challenges. In other words, those current techniques, you just eat them and walk by, and we don't get much better. But maybe artificial intelligence and machine learning can be that power-up that we need to help us overcome many of these testing challenges. Just maybe. And so, what is testing? And this is where, if I think about my expertise, I've been working in the testing space a very long time. And the more that I work in the testing space, the more that I realize that we are all very crazy for trying to test software. We're very crazy. You have to be crazy. Maybe that's why the developers don't have any percentage contribution towards that. But why do I say that? Well, when you're testing, you're selecting from an infinite domain some finite number of tests, right? So you have your program F, and you have your input and your output. And so you have this, what is really an infinite domain of inputs D, that somehow are mapping to outputs in your range R. And so on input input D, the program produces f of D. Not too hard. And as a tester, what we're asking when we test software is f of D an acceptable result? In other words, is f of D OKD or not OKD? Does that look familiar to you? What does that look like? Well, it looks sort of like this. It sort of looks exactly like what machine learning and training a machine was all about. And so there's a direct mapping between what we're trying to do when we judge or test software with what we do when we train machines. And so if anyone is going to get replaced by machine learning, it's going to be the testing part, right? Maybe. Again, I'm just forget that. Let's go back. So with this test, you take a subset of that domain, call it T, and you try to feed it to the program, and then you get your f of t's out of that. And then you're judging, and the whole goal, if the test is successful, then for all t in T, OKT. Right? Cool, our test passed. Now when our test passed, what can we do? What can we claim? Well, what we're trying to claim, if it's an ideal test, what we're trying to claim is that if T is successful, in other words, if that T, for all T, OKT, then we want to reason that the entire program is correct. That would be the ideal case, if we could select this subset and feed it to the program and somehow know that the program was correct. That sounds like insanity. No, it does. And if it doesn't sound like insanity, because you're a more visual person, let's look at it. Let's visualize the insanity. There's always this issue with coverage because there's usually a gap in coverage, right? In other words, there's no coverage because we're trying to do the impossible thing. And so imagine that you have an infinite input space, infinite number of inputs, infinite number of combinations of those inputs, and an infinite number of permutations of those combinations of inputs. Right? You start with that. But of course, if you have that situation, then you have an output space explosion problem, which means that input and output, well, that's all about state space explosion, which you're going to deal with next in a reactive system. And you're going to try to do that, and your manager is going to be like, yeah, but we got to ship the software. And so, yeah, this is the tester, and it looks insane, doesn't it? And so when we start talking about AI-driven testing, and when we start looking at the complexity, like we usually add features to software, and the complexity grows at an exponential rate. We add one feature, but then that feature, we add another feature, and that feature interacts. And so we keep doing that, and then all three features interact, and we start getting this exponential growth. But the way that we add tests today is very linear, right? And so there's this gap in coverage. And so for AI-driven testing, maybe we can leverage AI to somehow help us decrease this gap in coverage. All right, so the bots. These robots that we can train are actually here. You know, these are two solutions, one written internally by Ultimate Software and the other one from test.ai, that are using autonomous and intelligent agents, or these bots, to test software. And so what they're doing is that they're doing exploratory testing. They're trying things by trial and error. They're making mistakes. They're learning from them. They're using testing techniques. And they're generating tests, new tests every time, and trying to evaluate the results. So it's not some hard-coded script that happens every single time. And so this stuff is already happening. And how does it work at a high level? Well, you have some machine learning techniques. That's the core of everything. You have some interaction frameworks, these test drivers that interact with the system under test. And so somehow you need to come from some high-level test generation using machine learning to some low-level interaction. And then you can leverage the cloud to help you to scale this stuff. And so maybe several robots that are not so smart, they might be semi-intelligent, they may not be very, very intelligent, but maybe collectively they can give us a lot of gains when it comes to understanding the quality of our system and how well it has been covered from a testing perspective. And so there's a lot of benefits, right? The first benefit is that it's general purpose. Like AI can test software, any application, any domain you think about, you see that? That machine learning function is actually very applicable to almost any aspect of problems. And that's why you see AI being applied and machine learning being applied to every single domain, because it's a very general problem. Actually, a neural network with one single hidden layer can approximate any function, right? This also means that we can start to apply it to almost any application, right? It's not specific. Different types of testing. And it's what we call pesticide-free. There's something in testing called the pesticide paradox, which is really all about, if you run the same tests over and over, you get the same results, right? And actually expecting anything different is insanity, right? But here the AI is going to generate, and the machine is going to generate new tests every single time. And of course, if you want it to generate the same tests, you can, but it has this power. And then we have this scale, right? We have the power of deep learning, we have the power of cloud computing that helps us. And so this brings us to Act 1, so we can wrap up. And Act 1 is really about getting ready. Like, how did we prepare ourselves for artificial intelligence and machine learning in this particular space? Because how we prepare ourselves is very critical to its success in general. And so, if these are testers, well, and I mean that anyone that needs to test software, which includes developers, then artificial intelligence and machine learning are actually right here. And they're not caged up, actually. They're right in front of us. And if we don't start to get in front of this technology, it probably will take over. It'll be a serious problem. Because, you see, one of the key things, and Hollywood actually is good at getting it right a lot, right? They seem to predict a lot of things. If we don't start to worry about how these machines are tested, we're going to trust them, and they're going to fail, and they're only doing what we train them to do, right? And that's actually going to be very scary. And we're already trusting them for some things, and seeing that if we haven't figured out how to test them, it's going to be a problem. And why is it a problem? Well, the first thing to note is that traditionally when we program a system, we have inputs, we write our program, hopefully you write clean code, and then you have output. But with machine learning, you start with inputs and outputs. And the machine, this magic box, you kind of train it using those inputs and outputs. So you feed it that, and then what happens? This magic box gets updated. It's estimating your function, it's estimating your program. And what would we do if we change programs? What would we do right now when we change code and commit? We test it. So these machines are actually doing this stuff in the wild. Once you release this, it's learning, and it might become better or worse. And so we really need to start thinking about how do we build these systems with testing in mind. How do we build the machines to test themselves? And this is where what I studied in graduate school comes into play, where I was looking at how can we build testing into the runtime of systems, especially systems that are adaptive, systems that can heal themselves and configure themselves, and they need to have testing as an inherent part of their capabilities. And so we need to have bots to test the bots that might be inside causing adaptations. And so, even though we come here and we talk about AI-driven testing, it's important to know that this is really a combination of things. We have to think about testing AI and how do we design systems with self-testing in mind. And so myself and Jason Arbin, who's the CEO of Test.ai, actually formed a community. AI for software testing is that discipline. It deals with the intersection of those three circles that you saw. And what we're trying to do is bring together a community where we can study problems around these three areas. Because the only way that we're going to solve these problems and the only way that we can tackle these things is if we do it together. The problem is too important, too large, too much of a thing that we have to get in front of for us to think that one company or one effort is going to be able to achieve it. And so AItesting.org, please check it out. We send out a newsletter and try to keep on top of these things. So I have a talk right after this, right? It's now 10:30. I think it's at 11. I think you could check the schedule. But I'm going to go deeper into this stuff. Obviously, this is a keynote. It just scratches the surface of how you can leverage AI for testing. And so check that out. And now we're at the end, right? And it's cool because like this whole thing, Codecamp is all about community. And I think that y'all have the right culture when it comes to innovation, right? And so I'm actually very excited that I came here and was able to engage in discussions when I went to Yash, and then I went over to Moldova, and now I'm here in Cluj, right? And I know that Cluj is going to be the best stop, right? Because you saved the best for last, right? All right. So we're actually not at the end, but we're really at the beginning of this stuff. And so it's up to you to form that beginning. Thank you.
Thank you very much. Thank you, Tariq.